HMI Design Philosophy, Introduction. This section deals with the general rules related to the configuration of the DCS and the design of the HMI. It serves as the framework for the detailed design covered in later sections of this DP. The design of the HMI shall be conducted by a team of operators advised by an ergonomist and experts from other disciplines as required. Operating Philosophy. The DCS shall be configured so that the operator can work simultaneously in two different modes. Awareness. This mode requires the proactive role of the operator in controlling the plant. He monitors the status of the plant by paging through displays, watching trends and deviations, and taking action when required or prompted. Awareness is improved by a well-designed hierarchical arrangement and a logical and understandable grouping of the DCS displays. Exception. This reactive mode is triggered by events such as alarms. The operator's attention is demanded and directed by the system to displays where he can see what has happened and can take corrective action. Visualization of alarms and access to corrective controls depend on the urgency of action required. Process situations. The HMI shall be configured as follows for all operating conditions: steady state, running normally; perturbed or plant upset; pump trips, operating situation exceeds constraint, control instability; normal deviations or transients, startup, scheduled shutdowns, feed changes; at rest, plant stopped. The work activity, degree of vigilance, surveillance, and reaction time of the operator differ for each operating condition. The HMI shall be designed to assist the operator and all other users of the DCS in performing their tasks under all operating conditions. This involves specific displays and alarm handling strategies for the various operating situations. Controls shall be intuitive, and images shall be self-explanatory, leading the operator to the corrective actions needed to restore the plant to a steady state. Centralized HMI. The DCS interface shall be the centralized interface for all control and monitoring systems and subsystems, which may include ODS, optimization, IPS, FGS, tank gauging systems, machine monitoring system, QMIs, and CCTV. The operator requires access to the process and system parameters to carry out his tasks, and does not need to know the hardware origin of information displayed on the HMI. Status of instrument equipment subsystems shall be displayed in the DCS to warn the operator of subsystem malfunctions. Warnings should indicate the severity of malfunction and the course of action to be taken by the operator. Detailed diagnostics for maintenance personnel may also be displayed in the DCS if convenient and cost-effective. Otherwise, they may use other interfaces. Users and their requirements. The HMI, including ODS facilities, shall meet the requirements of all users: operators, panel and field, shift supervisor, operations management, support team, e.g. maintenance engineers, technologists. The list given is generic. Specific requirements for each product or site shall be specified for each particular user application using task analysis. Operators require clear, unambiguous displays and the possibility to take fast and flexible action. The HMI shall be configured with displays showing an overview of the overall operating situation, incorporating status, alarms, and data. These displays shall provide access to all other operator displays, allowing the operator to control the plant and manage alarms effectively. Needs to know what is going on and what has happened during the last shift. The HMI shall have displays and reports designed to accommodate this, including graphics showing major parameters, alarm status, controller status, sample results, and loss displays. Operations management requires information about the plant's overall operation and performance, provided via ODS displays accessible from site-networked personal computers. Support team includes maintenance engineers, reliability engineers, technologists, and project engineers. The information they need may be accessible via the ODS, but at least the following displays shall be configured within the DCS: identifying defective equipment, diagnosis of plant upsets, system maintenance, and modification of configuration and tuning parameters. DCS displays. Manufacturer's standard displays. Standard displays are default features set by the DCS manufacturer. They come in fixed panels or windows that can be accessed from graphic displays or other standard displays. These displays provide detailed information on instrument tags associated with or contained in the graphics. Operations and configuration teams should review standard displays early in the HMI design process to determine their fit within the overall HMI design philosophy. Standard displays typically include control group, displays an array of instrument faceplates corresponding to function blocks in the control station. It allows simultaneous monitoring and manipulation of process variables, PV, set points, SP, outputs, and modes, auto, manual, cascade, for groups of instruments. Each display can show up to 8 faceplates, identified by a page number or a user-assignable name. Trend group displays trend data for instrument tag parameters pictorially using multicolored trend pens. Each display can show up to 8 trend pens. Trend groups are categorized based on the sampling period and history duration, such as high-speed trends for critical monitoring, medium-term trends for general purpose, and long-term trends for plant performance. Summary: displays process alarms in the order and time they are generated, along with their status, acknowledged, unacknowledged, active. It allows acknowledgement of all types of process alarms, but a total acknowledgement feature should be avoided to prevent dangerous operation. Alarm overview provides an overview of active alarms in a matrix schematic format, mimicking a classic alarm annunciator panel. Alarms are indicated in functional group boxes until acknowledged. The boxes can be configured as targets to access graphic pages, the alarm summary page, or a control group. Graphic displays. Custom displays are built using graphic builder application programs on the DCS. They combine text, symbols, lines, patterns, graphs, and dynamic data with color and animation to convey additional information. Graphics usually depict process units schematically, showing equipment, process flow, and relevant control loops, along with dynamic data for process variables, alarms, and equipment status. Graphic displays are categorized as follows. Overview displays provide a high-level view of all process units controlled from a workstation, showing the status and mode of units with key performance parameters. They are used during steady-state conditions and do not show detailed equipment or instrument loops. FGS Area Overview depicts the plot plan of plants with FGS sensors installed. Alarms fill relevant plant boxes in red, yellow for revealed failure-robust initiators, and flash until acknowledged. Wind speed and direction are shown, and targets within boxes call up FGS plant overview displays. Detailed displays, steady state, show schematic views of process equipment within a subunit, including dynamic data and control options for the equipment. Short duration trends for major control loops are included for shift change and subunit analysis. Detailed displays, transients, reconfigured steady-state process graphics to cater for specific transients and modes of operation, such as startup or process upsets. They assist operators in visualizing and managing the phases and effects of these transients. Multivariable control loops show schematic views of multivariable control schemes, including process variables and tuning parameters for diagnostic purposes by technologists and control engineers. Sequence displays graphically represent control steps and their states for particular equipment. They include windows with sequence steps or guidance messages for operators during issues. IPF logic status. Schematic representation of IPF logic, displaying the status of individual IPFs and override facilities. First failure alarms are displayed, acknowledged, and reset here, and the logic status is used for trip analysis and troubleshooting. Display page allocation. Displays should be grouped systematically, with specific page ranges allocated to process units. This organization facilitates easy navigation and future expansion. For example, crude distiller, CG01099, TG01099, GR01099, platformer, CG100 to 199, TG100 to 199, GR100 199, hydrocracker, CG200 299, TG200 299, GR200 299. Utilities CG300 to 399, TG300 399, GR300 399. Display navigation. General DIS in the DCS can be accessed using console keys or through targets configured within the graphics. Navigation through different displays to take action resulting from an alarm should be achieved by a maximum of 3 commands. During the design and configuration of displays, clear navigation rules should be developed to ensure a consistent and structured approach in moving from one display to another. Stack display navigation and command tools. Function keys. Function keys are one-touch operation keys that can be configured to call up displays, windows, faceplates, and initiate sequences or application programs. They minimize the typing of frequently used commands and requests, reducing the time required to access a display or initiate a sequence. They also reduce the memory load of the operator and the risk of typing errors. Function keys should be arranged logically and consistently to clearly indicate their purpose. Secondary confirmation should be required for initiating sequences or application programs to prevent inadvertent entries. Function keys are equipped with LEDs that can be configured to aid the operator in responding to alarm conditions. Targets. Targets are areas within a graphic display that can be configured to call up displays, windows, faceplates, and initiate sequences or application programs. They have the same functionality as function keys, but are configurable for every graphic display. To ensure ease of operation, the target area should be at least 2 centimeters on touch targets. Smaller targets may be considered where trackball or mouse pointing devices are used. Generic targets should be considered for navigation purposes and consistently positioned in the screen. These may include calling detailed displays, help windows, toggling control lines, trend displays, etc. ODS displays. ODS displays are mission-critical but rarely time-critical. Therefore, the aspect of human error reduction is less important. The guidelines and conventions used for configuring DCS graphic displays, where applicable, should also be used for configuring ODS displays. Where similar displays are available on the DCS and ODS, a clear distinction should be made to avoid confusing the operator, especially if they are shown physically next to one another. Task analysis should support which displays should be allocated on the DCS and ODS. Guidelines for graphic display building and configuration. General. This section promotes a consistent layout and configuration of graphic displays. It provides guidelines on how graphics should be built and how to present information effectively. Density of information on screens. Graphic displays should not be cluttered, as excessive information may lead to extended search times by the operator and loss of clear direction. There should be no more than 40 live data points per display. HASH generic graphic template. Specific areas of the screens should be reserved for certain kinds of information, such as graphic titles, navigation targets, and command zones. These areas should be consistent across all displays and should be developed in a generic graphic template. Graphic title, preferably in the upper left corner of the screen. Navigation targets, consistently positioned to allow natural progression from one screen to another. Command zones, reserved for instrument faceplates or change zones to enable control changes by the operator. Information flow. Screens should be organized to allow natural progression from one area to another, typically from left to right and top to bottom. Layout for process scheme displays. Graphics should be logically built from major process equipment, e.g. vessels, columns, pumps, compressors, and control schemes. They should be oriented from left to right, with pipes or signal lines entering from the left and leaving on the right. Crossing pipes or signal lines and unnecessary details should be avoided. Process equipment that cannot be controlled, e.g. isolation and bypass valves, should not be shown unless necessary for task understanding. Displays should be task-driven, showing major equipment control aspects and avoiding use of the outer edges of the screen, which may be obscured. Configuration standards. Colors. Color usage should be conservative to avoid clutter and strain on the eyes. Prominent colors should be reserved for urgent situations. Color should not be the sole means of distinguishing important items and states. It should be used together with other highlighting features. Typical color conventions include red, high priority alarm indication; yellow, medium priority alarm indication; green, healthy logic signals; cyan, magenta, white, various normal and fault indications. Text. Text should primarily be in lowercase with only the first letter of the first word capitalized. Uppercase should be used sparingly for titles and headings. Text should be left justified and broken into sections for readability. Labeling. Labels should be unique, meaningful, and descriptive, placed adjacent to relevant items. Each graphic display should have a title in the top left-hand corner. Data labels should be distinct from data items and should include units where applicable. Tables. Data in tables should be aligned vertically, with alphanumeric data left justified and numeric data right justified. Columns should be separated by adequate space or lines, with headings clearly distinguished. The order of information should be logical and based on user needs. Windows. Standard windows are useful for extra or detailed information without using another screen. Types of standard windows include Alarm window, shows a list of recent alarms. Instrument window, displays instrument faceplates. Trend window, shows trends of instruments. Message Help window, provides operational assistance. Short duration trends should be used within schematic graphics for key process parameters. Controller parameters displayed in graphics should be limited to PVs at overview levels and may include SP, output, and modes at detailed levels to assist operators. By following these guidelines, the HMI design ensures a consistent, efficient, and user-friendly interface for operators and other users. Alarm management. Introduction. This section describes the methodology for designing alarm management, assisting in setting an alarm philosophy while utilizing the default features and capabilities of the DCS regarding alarm management. Advanced alarm management through non-DCS features is not covered. Approach to alarm handling. A flowchart outlines the general approach to alarm handling design. Details of individual steps are discussed in subsequent sections. Multidiscipline team to analyze alarms. Tasks of the multidiscipline team include documenting the alarm philosophy, analyzing each alarm, establishing grouping or masking, and implementing applicable alarm management features. The team should consist of panel operators, process engineers, instrument engineers, and other specialists as needed. Alarm philosophy. An alarm philosophy provides guidance for establishing the purpose, use, and need of alarms, with rules for prioritizing and presenting alarms. Alarms are intended to minimize deviations in plant equipment and processes from developing into significant hazards or disturbances. The priority of alarms should assist operators in handling multiple alarm situations. Priorities are based on consequences to plant systems, urgency of operator response, and DCS functionality. Alarm analysis. All alarms should be analyzed for accuracy of their settings and assigned priority levels. Required materials for alarm analysis include the Alarm and Trip database, PEFs, control and IPF narratives, and IPF classification results. Criteria for urgency of action and consequences are defined to assign alarm priorities. Alarm configuration. Features of the DCS relating to alarm management include alarm detection, priority levels, deadband and signal filtering, suppression, and auto acknowledgement. Configuration standards should be developed for each feature to ensure consistent application across the plant. Alarm detection. Alarm detection functions for instruments are configured in the Control Station Builder. Only tags indicated in the alarm and trip listing should have enabled alarm detection functions. Alarm priority. Default alarm priority levels range from high to low priority and recording alarm. Assignment of priority levels should align with the defined criteria and DCS functionality. Alarm deadband and signal filtering. Deadband settings should prevent oscillating alarms and keep alarms present for appropriate durations. Filter parameters should smooth input signals without affecting control dynamics. Alarm suppression. Alarms can be suppressed, masked, or unsuppressed, demasked at the DCS HMI. Static alarm suppression is implemented via sequence blocks based on process conditions. Active alarm suppression depends on predefined process conditions or events. Alarm auto-acknowledge. Alarms can be automatically acknowledged based on predefined conditions or events. Auto-acknowledgement is useful for subsequent expected alarms after a primary alarm has been activated. Alarm grouping representative alarming. A standard function block can generate a common alarm for a group of instruments, preventing confusion with individual alarm details. Representative alarming can be used in conjunction with graphic displays to prevent alarm avalanches. Active alarm limit setting. Alarm limits can be dynamically changed via calculation and sequence blocks based on predefined conditions, useful for startup sequences and various product runs. Alarm presentation, graphic configuration. Alarm information should be presented in a user-friendly manner, with clear descriptors and visual indicators of alarm status. Representative alarming and dedicated graphic pages for alarm suppression can enhance alarm management. Audible alarm. Different audible tones can be configured for alarm priority levels. High-priority alarms should have a continuous tone, while medium and low-priority alarms should have an intermittent tone. The volume should be adjustable above the control room background noise level. Alarm handling techniques for plant operating conditions. Different alarm handling techniques should be applied based on plant operating conditions, such as active alarm suppression and auto-acknowledgement for steady state and upset conditions, and static alarm suppression for plant shutdowns. Console design. Operator interface. Layout of consoles in the control room. Future expansion should be considered when determining console layout. The setup should conform to the process path and local preferences, left to right or right to left. Consoles should be functionally grouped according to process sections. The layout can be U-shaped or C-shaped, depending on the number of operators and functional links between processes. The process flow and communication flow between operators and consoles should be coordinated using link analysis. Refer to ISO D11064-3, ISO DS92413, and ISO 9922415 for different console layouts and their advantages and disadvantages. HMI console types. Two types of HMI configurations are available for the DCS, freestanding and desktop workstation types. Freestanding type, VDU, keyboard, and pointing device are fixed on the console chassis. It offers less flexibility for HMI arrangement. Desktop type, VDU, keyboard, and pointing device are separate items placed on tables to form a console. It offers more adaptability in the arrangement and is less expensive, allowing easier maintenance. The workplace should meet general anthropometric requirements. Number of HMI consoles. A set of continuous process units with 200 to 400 control valves should have main console, 4 VDUs, 2 keyboards, 2 pointing devices, a communication panel, a hardwired switch panel, and a CCTV panel. Secondary console, 2 VDUs, a keyboard, and a pointing device used during startup, certain maneuvers, or disturbed states. Supervisory console, 1 VDU keyboard pointing device configured as read-only can be switched to read-write with authorization. Used by technologists, operations management, and engineering for checking plant operability, parameter modification, process control, diagnosis, condition monitoring, and system maintenance. The main console HMI should include a hardwired switch panel with individually labeled and logically arranged ESD switches, depressuring switches, and MOS enable switches. Operational override switches should be avoided by using automatic timer functions in the IPS. Communication panel. The main console HMI should include a panel for radio, telephone, and intercom equipment. Consider installing voice-activated or foot-activated headset microphones to free up operators' hands and reduce control room noise levels. CCTV panel. The main console should include a panel for CCTV controls. The CCTV display can be incorporated as a window on the DCS screen or on a dedicated monitor. The monitor can be mounted within the main console, on a dedicated console, or suspended from the ceiling. Panel. No hardwired alarm display panels, ADPs, should be applied, except for the FGS Mimic panel, which may be included in the main HMI console or mounted on a dedicated console. Printers and video copy units. Alarm event printers and video copy units should be mounted on separate furniture from the main HMI console to minimize noise and distraction. Consider PC-based alarm archiving to reduce printer use and maximize data interrogation capabilities. Console dimensions and shape. Console dimensions depend on the physical dimensions of the working population. Work surface height should accommodate both men's and women's dimensions. Absolute dimensions should be determined by consulting anthropometric tables. Adjustable workplaces should accommodate 5th to 95th percentile body dimensions. Controls should be within reach and not positioned above the shoulder height of the 5th percentile. Input devices should be freely movable over the work surface. Control room lighting considerations. A lighting plan should be developed based on the layout of HMI consoles. Lighting specifications should cover illumination levels, color schemes, fixture positioning, and luminance of surrounding surfaces. Light intensity adjustments should be considered. Control room lights should avoid causing reflections on VDUs and keyboards. Strategies for existing sites include selecting suitable fixtures, changing lighting positions, and shielding sources of glare. VDUs and associated criteria. High-resolution VDUs should be used for graphic symbols, with a resolution of at least 1024 by 1024 pixels or 1280 by 1024 pixels. Image refresh frequency should be 70 Hz to avoid flicker. Contrast and brightness should be adjustable. HMI maintenance. Integrity. Integrity of HMIs shall be managed as follows. For the DCS, authorized personnel shall be appointed to manage HMI integrity. Principles and practices of system management shall be applied. HMI hardware modifications shall be carried out in accordance with plant change procedures. Software change procedures shall be instituted as described in the respective section. HMI software configuration changes shall be carried out in accordance with the software change procedure. Modifications following a software change shall be immediately documented using the self-documentation features of the DCS. Temporary modifications, such as setting off an alarm, shall be separately identified within the software change procedure. A focal point for DCS manufacturer maintenance and support shall be appointed. System software revision and upgrades should be avoided. If required, procedures specified by the manufacturer shall be followed. All revisions shall be documented. Backup of system files shall be made whenever changes to the system are implemented following a software change. A procedure on maintaining backup media, e.g., number of copies, last date of backup, and storage location shall be developed. System documentation shall be available. Security and access rights shall be documented. Software copies of graphics shall be available. Software change procedure. Software change refers to the modification of the existing software configuration resident in the DCS. This may involve changing the functionality of control loops, changing parameter settings, deletion or addition of instruments, changing security and access level, modification of graphics, etc. To ensure that a proposed software change will not compromise the integrity of the DCS and the process plant or equipment being served, a procedure shall be instituted to establish a consistent methodology involving relevant parties to evaluate a proposed software change before implementing it in the DCS. System security and access. Security features shall be configured in the DCS to minimize the occurrence of operational mistakes and/or unauthorized changes in settings. These include restrictions in the range of operations and monitoring display functions. During the configuration of the DCS, security levels covering parameter changes and access to the HMI should be assigned for individual instruments or groups of instruments, e.g., operator level, supervisor level, engineering level. Modifications in standard and graphic displays should only be allowed at the engineering level. Access to security levels shall be controlled via passcodes or key locks. Procedures shall be instituted covering authorized holders of keys or passcodes. Hardware maintenance. Time and condition-based maintenance schedules, such as degaussing of screens and CRT replacement, should be followed to ensure the quality of displays in the HMI